Hello and welcome to my Physics 2212 Lab 6 Magnetic Braking with Faraday. The purpose of this lab is to gain a deeper understanding of Faraday's law and magnetism by observing a magnet falling through an aluminum tube. The two physics principles used are Faraday's law and the magnetic field of a ring, with their formulas given in the slide. A brief preview of the results is that the real fall time was 0.876 seconds and the simulated fall time was 0.983 seconds. The assumptions made in this lab are that the tube behaves like many rings stacked on top of each other, that the magnet falls perfectly straight through the tube, and that the system is ideal. The system is the magnet and the aluminum tube, and the surroundings include everything else, including the Earth. In the middle, we can see a diagram of the experiment. The procedure was as follows. First, drop a magnet in the aluminum tube. Then measure the amount of time it takes to fall. Repeat this 5 times and calculate the average fall time. In our experiment, the average fall time was 0.876 seconds. For the computational model, first I set the length, width, and inner radius of the aluminum tube as seen in the first image. I also set the properties of the magnet as seen in the second image. In the third image, I used the formula for the magnetic field of a dipole that is in the right to calculate the magnetic field of a dipole. To calculate the derivative of flux with respect to time, I used the formula that is given in the video. Then I calculate the gravitational force and the current in the ring using the standard formulas. Then I calculate the magnetic force on the ring by the magnet using the formula for the magnetic force. Then I calculate the net force on the magnet and finally update the velocity and position using their update formulas. As we can see, the velocity initially drops to approximately minus 0.5 meters per second, and then it remains constant until the end. The simulated fall time is 0.938 seconds. A similarity between the computational model and the experiment is that both of their fall times were within the same order of magnitude. However, there was a 0.1 second difference between their predictions. Some sources of error include that in the experiment, the magnet does not fall perfectly straight, that the aluminum tube is not a perfect cylinder, and some human error in measurements. The first additional question is what if the resistivity of the conductor were reduced as close as possible to zero? The answer is that it would take the magnet longer to fall because a lower resistance means a larger current is induced, which in turn causes a larger magnetic field and therefore more resistance to motion. The second question asks what if holes or slots were cut into the tube and how this would affect the ring currents in my model. In this case, it would fall faster because the current would flow around the holes, which means it would not follow a ring shape, which would reduce the magnitude of the induced magnetic field, creating less resistance to motion.